Hello, dear Abaqus users. In this video, we will present the details of the project titled Analysis of Dynamic Response of Ballasted Rail Track Under a Moving Load. Okay, let us provide a brief overview of the project's main focus and the desired outcomes.
Basically, this was a part of a research project which I was doing in IIT Delhi. The overall topic is like we try to define the critical velocity, and critical velocity or critical speed of a rail track is almost similar to resonant frequency, or the frequency or the motion speed at which we have the highest vibrations. So if we like run this simulation, we get the highest vibration, and we can judge this highest vibration so that we don't run our trains higher than that speed. So at which we can get the speed at which we are getting the highest vibration. This model also give you the dynamic amplification factor. So for example, if you are running your train at 50 kilometers per hour, and then again you are running your train at 100 kilometers per hour, so you can expect how much vibrations the train will face when it runs at a higher speed. So this model also helps you to get those dynamic amplification factors, and I have also published an article about that. So how you get this from this model. So these are the two major aspects of using this model, which you can learn and like use in the industry. There are other things which people have used this model is like track degradation, but I haven't used this on this, but people have been like trying to use this model for track degradation in IIT Delhi, because I left and I gave it to some of them, but like I have to see their success when their publications come out. But yeah, these are some of the aspects.
It was a brief review of the project specifications. Now, let us delve into the Abaqus CA model for a better understanding.
Part instances. So I created this wheel as a one part, then the rail as one part, then sleeper, one sleeper as one part, but I created a pattern of the sleepers and then merged all of them. And yeah, after merging, they are again a single part. Then this middle ballast or the finite ballast as one part. Then we had this other infinite part, as you can see, they are in gray. Further I will show you them here. So the gray ones, infi1 and infi2, they are shown here. The infi2 is it's visible on this side, and the blue is infi2, which is, I think it's visible on the other side. Yeah, this blue one, as you can see, this blue is infinite. So I have named them based on what they are basically doing. So infi1 and infi2. Then we have this infi long, which is on the other side, which is this longer side of the model. And then we have infi bottom, which is not visible from here, I think. Yeah, it's visible, but it's like this. So this is infi bottom. So infinite layers, but there are other materials, other parts which I have created, which is like, instead of creating partitions, I created whole different parts here, which, as you can see here in the middle, where I used much finer mesh. So these are the different other parts, and you can see them here in the part instances: ballast 1 and ballast 2. Then we have ballast mid, which is the this red part. So ballast 1 and ballast 2 are the on the other side of this central part. We have created one ballast, and then on the other side we have ballast 2. So you can see them by the color. The green one is on the other side and the white ballast is on the other side, but basically they are the same materials, just different parts instances, not like they have different properties or anything. It's just to make this model more complex so that I can create a more finer mesh at the center. But it's basically simple. That's why I was creating this Python file, which will look much more simpler. So that's how the assembly looks like. and these are the parts. Yeah. So there are basically 5 materials which I have used, but the underneath layers are ballast, subballast, and subgrade, which are the ground layers. So ballast or middle of the geometry, which has a relatively finer mesh, and there is a wheel somewhere. Just zoom it out and show you the wheel. So there is a wheel. So I had different models where I ran multiple wheels. I also created a whole rail car, but like for my research, I only used wheel because I was more concentrating on geotechnical aspects. So that's why I used wheel. But I know how to use a rail car as well. But like I have to brush it up anyway. I haven't used it. So this is in this model, it's just wheel and then this rail track model. And I'll show you the mesh. So this mesh, as you can see, it's pretty general, but at the center or at the middle of the railway track, it becomes a bit finer, as you can see here. Here, because I'm recording my data here. So the sleepers, the rails, and the layers like ballast, subballast, all are like relatively finer mesh, finely meshed. Now uh, this outer boundaries in this model are all infinite boundaries. I will show you the element types. So these element types, as you can see, are different. The blue ones, I'll show you the colors. The blue ones are acoustic mesh. I don't know if this window is, yeah, acoustic mesh, which we change in the input file. So this is the model which I have already created. The load is there, boundary conditions are all in place, interactions are all in place.
That was all you needed to know about the model properties. But have you thought about how to define infinite elements for the model? To do so, you need to write the INP file, correct it, and then start the analysis from the corrected INP files. How do you do that? We will explain it in the following.
To run this simulation, what you need to do is that you need to go
Infinite elements. So let us show you the results.
click on the results, and this results, as you can see, the wheel has started running. I will show you the frame wise output. Yeah, it's here. Let me just move this frame to here. Well, let me also zoom in. So as you can see, this wheel has has an applied point load at the center, and we start from the 0, and then we keep clicking on this, and we see that this wheel has started moving, and the wheel motion in this specific output database is being run at 600 uh, kilometers per hour. So it's pretty fast, and that's why we are recording our output database in similar fashion as I've showed you in the input file. So you can see this wheel keeps on running, and that's how we get this uh, different deformation in the rail. But it's not like we are seeing this stress field in the rail if we remove, because relatively we don't see much deformation in this other layers. So for example, if I guess remove the rail instead of elements, I have to scroll down and then part instances, and I select the rail. Okay, I should done. So you can see now once I remove the rail, the deformations also are visible on the sleepers. Sorry. Uh, For example, now if I remove the sleepers, click on sleepers, I click on done, I remove the sleeper, I can see the deformations in the other layers as well. The wheel is rigid, so we don't see deformations in wheel. I have applied rigid boundary conditions to wheel. So as you can see, there are deformations in all the layer, but it's just the matter of perspective.
Hello everybody and welcome to our new video training package of Abaqus. Dynamic response of ballasted rail track under a moving load. Introduction. Analysis of dynamic response of ballasted rail track modeling. Analyzing dynamic response and critical speed of rail tracks. Results? Thank you for taking the time to watch this video. We hope it will be useful for you.